So in the last lecture we started discussing about the advantages of particle towers, where are they being applied. So we already said that they can be used for three main usages. One is it can be used as an anchor platform for transporting ships or vessels. It can be used as a temporary base in naval application. It can be used as a pipeline supporting system or riser support systems, which is commonly used. However, the tower being supported or the deck being supported on a single tower, it has got a lot of action in terms of rotation, which was undesirable. So people extended this by having multi legs which are parallel. We already saw the advantages, the design concepts evolved by MLAT. Now to write the equation of motion to MLAT or to solve, let us try to see and understand very clearly that researchers have showed in the recent past that response control of MLAT is mandatory, because they give a lot of excitation to the top side, and if you are able to control the response to some extent, then one can improve the usage or the functionality or the operability of these towers, not only by having multi legs but also by having response control systems. Before we move on to multi leg AT, let us quickly talk about multi hinge and try to see how I can derive the equation of motion, then how I can solve. Just an introduction to that for a few minutes, then we will move on to MLAT, where I will focus on response control algorithm directly, and we will see how we can do that. So now to understand multi hinge, we already said that I have a hinge at the bottom which can be identified as a universal joint which is having a spring, which is, why it is spring, because it is having a rotational stiffness m theta. So if it is a single tower, it is AT, if it is multi tower, then it is hinged, and so on. So these are the points where the hinges are located, and so on and so forth. So it is such an inverted pendulum actually. So let us take up an example of an inverted pendulum of 2 degree quickly, try to write the equation of motion for that and assimilate that with this easily. It is easy for us to do that. Okay. Let us take up a 2 degree freedom system, a simple pendulum which is suspended like this. Let us say a hinge. Let us say the mass is lumped here. Mass is lumped here. So let us call this as theta 1 and this as theta 2. This of course as m1 and this of course as m2, and L1, L2 and so on. We know that the velocity vector of this, which I can call as V1, which is simply equal to L1 theta 1 dot. I can also write down the velocity for this in a simple vectorial notation like this. See how we are doing it. I draw a line parallel to this, because I understand, you know that this is going to be normal. Okay. So I draw a line parallel to this here. Obviously this will not be normal to this because they are not parallel. So I draw a line parallel to this here. I presume that they are parallel. Okay. I mark V1 here. That is the velocity of the first particle. I draw another line which is parallel, normal to this from this point. These two are normal. Okay. So I rewrite this slightly in a different manner. This is going to be L1 theta 1 dot, and this can be L2 theta 2 dot. I complete this parallelogram and get my resultant vector, which is actually my V2. Okay, this is V2. The angle between them will be theta 2 minus theta 1, as the relative angle between the initial and the final position. Okay, this angle. The angle between these two will be theta 2 and theta 2 minus theta 1. Theta 2 is larger than theta 1. I can apply a simple cosine rule and write down this V2. Okay. Let us do that. So V1 is going to be L1 theta 1 dot, whereas V2 square will be using a cosine rule. We already know a cosine rule. If I have, let us say this is A and this is B, I should say A square plus B square minus 2ABC cos include angle between A and B, that will give me a resultant of this, is it not? Similarly, I do it here. L1 theta 1 dot square plus L2 theta 2 dot square plus 2 L1 L2 cos theta 2 minus theta 1. Okay. So, simple cosine rule. Now, we know for the system the kinetic energy is half m1 v1 square, that is the mass m1, plus half m2 v2 square, and the potential energy of the system, let us say PE, let us say KE, is m1 g L1 1 minus cos theta 1. We all know that because this is going to be L1, this is going to be L1 cos theta 1, the difference of these two, is it not? This difference, okay? L1 minus L1 cos theta 1 plus m2 g of L1 1 minus cos theta 1, L2 1 minus cos theta. This is my potential energy, this is my kinetic. I will call this as, let us say, equation 1a, equation 1b, equation 2, equation 3. Okay. Now, we know using Lagrange's relationship, I can write the equation of motion energy method. It says that d by dt of dou kinetic energy of dou qi dot the partial derivative of potential energy of qi minus partial derivative of kinetic energy of qi should be set to 0. So, let us try to find out the partial derivative of kinetic energy with respect to q is the degree of freedom. I should say this as theta 1 dot. There are 2 degrees of freedom, theta 1 and theta 2, where the displacement and velocities are displacement is theta 1, velocity is theta 1 dot, and acceleration is theta 1 double dot. So, let us write down the equation for kinetic energy first, which is half m1 L1 theta 1 dot square plus half m2 L1 theta 1 dot square plus L2 theta 2 dot square plus 2 L1 L2 theta 1 cos theta 2 minus theta 1. This is already square, okay? See, this is square already. So, need not have to square again, but this was not square, this is V1 only. So, I have squared it here, okay. So, let us expand this. So, let the kinetic energy be expanded as half m1, let us say L1 square theta 1 dot square half m2 L1 square theta 1 dot square L2 square theta 2 dot square plus 2 L1 L2 cos theta 2 minus theta. Now, I have to partially differentiate this with respect to theta 1 dot, okay, that is what I have to do. which I say half m1 L1 square 2 of theta 1 dot plus half m2 L1 square 2 theta 1 dot plus L2 square 2 is going to be 0 anyway, some partial derivative, plus 2 L1 L2. Please make a change because this is L1 theta 1 dot, this is L1 theta 1 dot, this is L2 theta 2 dot, this square plus twice of AB cos. So, I am missing here theta 1 dot and theta 2 dot. I am sorry, I am missing that here. I think we have to make those everywhere. Okay, theta 1 dot and theta 2 dot. So, here theta 2 dot will stay cos theta 2 minus theta, because the derivative is respect to theta 1 dot. So, simplify and give me what is dou kinetic energy by theta 1 dot. So, m1 L1 square theta 1 dot plus m2 L1 square theta 1 dot plus L1 L2 theta 2 dot. I can say this set to 1 because actually theta 2 minus theta 1 will be very less, and practically that cosine angle will be practically equal to 1. Now, I want to find the differential of this with respect to time, because that is the equation required in Lagrange. Okay. When I do that, it will become m1 L1 square theta 1 double dot, that is the derivative I will have, plus m2 L1 square theta 2 1 double dot there is m2 missing here, this m2 is a multiplier here, okay, plus m2 L1 m2 theta 2 double dot. Okay. Then similarly, we can find the partial derivative of potential energy with respect to theta 1, partial derivative of potential energy with respect to theta 1. Can you give me this value, because potential energy equation is already here with respect to theta 1. So, m1 plus f2 GL1 sin theta 1 is okay. So, I can write the first equation of motion by substituting in the Lagrange's. Can you give me the first equation of motion? Substitute that and give me the first equation of motion. m1 plus m2 L1 square theta 1 double dot, that is the first term you will get, plus m2 L1 L2 theta 1 double dot, it is here theta 2 double dot, theta 2 double dot, no, yeah, theta 1 goes away, plus of course the value here, which is m1 plus m2 GL1 sin theta 1. For lower values of theta 1, I can simply say this as theta 1 itself, okay, set to 0. Let us just look at this equation. Now, I write a similar equation for a 3 hinged MLET. Okay. Let us look at this equation and try to generate a parallel mass matrix for a 3 hinged tower like this. Okay, they are not parallel, this and this are not parallel, they are hinged. So, there are some spring restraints here which are those universal joints. I call this as m1 delta 1 displacement, m3 delta 3, and the rotational stiffness I call this as k theta 1, this as k theta 2, this as k theta 3, where theta 1 of course is with respect to initial vertical to the center, this is theta 1, and so on and so forth. If I enlarge only one element and try to draw it here, we know an element will have a buoyancy chamber which is slightly larger, let us say this is my hinged point, universal joint. Let us say I have a center of buoyancy here and mass center here, okay. This is center of buoyancy, this is center of gravity or the mass center. We already know it is for stability, this is important. I call this distance from the hinge as L1B. L stands for the length, 1 stands for the number of the member, and B stands for the buoyancy center. So similarly I would call this as L1G. If I really wanted to find a force at any point on this member where the force is acting as F1, I would call this distance as LF1, because I want this for a moment on the right hand side of my equation of motion, and of course I will call this entire length as typically Li, in this case L1. Can even L1F for maintaining the similarity, L1B, L1G, L1F and L1. It is a typical configuration or geometric configuration of a member. Similarly for member 1, member 2, member 3 all will be same, except that the suffix 1 will all replace by 2 and 3 respectively, okay. Now I want to write a mass matrix copying from there directly, okay, without deriving it. So we all know, being a 3 degree, because there are theta 1, theta 2, theta 3 independent rotations, they are not dependent on each other. So the mass matrix will be 3 by 3. Okay, with 3 by 3. I can write here, if there are 2 members M1, M2, there are 2 here, I can write here M1 plus M2 plus M3 of L1 square. To make it very precise, let us expand this. This is what I must get similarly from here, but I want to expand this slightly. Let us rewrite this equation slightly in a different manner, like here. It will be M1 L1G square. For M1 it is L1G actually, okay. For M2 and M3 it is only simply L1 and L2, right. So it is going to be M2 L1 square and M3 L1 square, okay. Because we borrow the same term from here, sum up all the mass, that is what I will get here, right. In addition to this, I will also have the moment of inertia of this system itself alone. In the earlier case it was neglected because spring mass system having a neglected mass of the self body, but here this is present, therefore I should say plus I1, okay, where I1 is the moment of inertia of this system itself, because this is now substantially high, we cannot neglect this. In the pendulum problem we neglected it, but here cannot neglect, okay. Similarly, can I fill up this? So I should say M2 L2G square plus M3 L2 square plus I2, where I2 is the moment of inertia of the second member. If I want to do this, this will be M3 L3G square plus I3, okay. I have borrowed this exactly from this. Now let us look at this term, the second term, which is related to theta 2, whereas there are 2 only, but it will be theta 2 and theta 3 both, theta 2 double dot, theta 3 double dot, second term. Now if you have only M1 and M2 mass, M1 is not appearing in the second term, M2 is appearing, whereas the product is L1 and L2. In this case going to be M2 and M3. Okay, let us expand this slightly. Now let us rewrite this. This is going to be M2 L1 L2G, because I am talking about M2. Okay, M1 L2 L1 L2, so L2G, plus for M3 this is going to be only M1 L2, there is no G, the same term here, same term here. If you write the second equation, you will know it is going to be symmetric. Okay. The third one will be, can you give me the third one? Can I write this as M3 L1 L3G? Same here. Now I can quickly fill up this. Can you give me this value? Okay. We have the mass matrix ready. So we can derive the mass matrix for a multi-hinged tower like this. So I took up this example only for you to understand how the terms related to theta 1 double dot and theta 2 double dot will appear. Of course, this term will appear in the stiffness matrix, is it not? Because that is related to theta 1 displacement. Okay. I will give you a very simple method to derive the stiffness matrix. Give unit displacement here, get alpha 1 1 2 1 and 3 1 and invert it to get k. Okay. I mean, give unit displacement here and try to find the influence coefficients in the single manner, in the earlier manner what we explained. You will get the alpha matrix, which is 3 by 3, invert that, you will get a k matrix, which I am not writing it here. There are papers which will refer back in the presentation. You can see that you will exactly have the same mass matrix and same k matrix available in the paper. Okay. We will move on now to, now once I have k and m matrix, C is going to be 2 zeta omega m, the classical damping matrix. I have the equation of motion now set for my problem. I can solve this using any iterative scheme, which I have not so far discussed. In the last case also we had a similar problem, we have not discussed. We are holding the iterative scheme later, we will discuss all of them at the end. Okay. So now equation of motion is now complete, I can solve them if you know the iterative scheme. Okay. Let us hold it here, come back to the response control of the system now. Okay. Now any doubt here in simulating how we are getting the mass matrix, how we will get the k? I am leaving it for a homework to you. You should be able to do this, because if you are able to derive the first column of the influence matrix or the whole matrix, you can easily invert it and get the k matrix, which will be exactly similar to what you have there in theta 1, theta 2 and theta 3 terms, which you will appreciate. Okay. If you have still doubt to compare, you can always look at the papers, which I will refer back now. You can look at the papers. Of course, the derivation is not shown in the paper. You will have only the mass and k matrix given in the paper. You can compare them and find out. Okay. But the derivation comes from here like this. So instead of writing this matrix directly from a 3 hinged tower, I have picked up a 2 pendulum system problem and I derived that value for you. Then I just picked up the same idea and extended it for a 3 by 3 n by n system. Okay. It is very easy to understand, right? That is the reason why I have picked up that. So we hold it here, we get back to the response control. Any questions here? Any questions? Okay. So in the last lecture we appreciated that for deep waters from shallow to medium depth, offshore platform designs have been formulated to have a compliancy introduced in the design. The compliancy introduction will also cause increased flexibility. Therefore, the system should have a recentering capability. When the system is pushed by a lateral force, there should be a recentering element in the system which will try to bring it back. There are 2 elements present in an MLAT. One element is the spring or the universal joint, which has got M5 characteristic. For any M given to you, it will bring it back in the opposite direction. One. The second could be the alteration of the floating chamber, which is nothing but the buoyancy chamber. Because of variable submergence effect, the buoyancy chamber will also try to bring back the system. But however, it has been noticed with researchers, as he presented in the last slide or last lecture, that the response of the top deck is sufficiently large, therefore these platforms cannot be used for production facilities. Okay. So there has got to be recommendations made by the researchers saying that let us try to attempt response control mechanisms on this. Now let us look at the real structural engineering where response control or where are they applied, what are the different concepts available. Out of the concepts available, what I will pick up for this problem, then I will show you a video that how this works out, then I will again derive the equation of motion for an MLAT with a tuned mass damper, then I will solve this here, leave the equation of motion, show you the results directly. That is the idea of this lecture. Okay. Let us see now what are the different response control mechanisms we have in the system in general. Let us talk about response control of multi-leg articulated towers. There are different systems available in general: passive control, active control. Passive control actually alleviates energy dissipation demand on the primary structure by absorbing the input energy, therefore reducing the possible structural damage. That is called passive control. Active control is you have to give a control mechanism to the system where the control mechanism also receives external forces. Okay. Passive control does not demand external input to the system, whereas active control demands an external input to the system. Okay. You have got to, for example, if I want to push a larger mass, I have to pull the mass back by an external supply, which will again needs a tremendous amount of energy, right. So, you need an excitation force, you have a structure, you have a response, whereas you have a control mechanism there attached to the structure, which can be either passive or active. The active mechanism comes like this because there are sensors available, excitation is given to the structure, structure responds, the response is sensed with the sensor, the computer controller receives the sensor, activates a controller which gives an opposite force to the structure to stop the structure. Okay, that is called active control mechanism. So, in this loop you will see that the control sensors or the control actuators require a lot of energy to dissipate the response of the structure in an opposite direction. Okay. In case of power failure, let us say, in case of sensor fail to recognize the response, in case of there is a phase lag of the sensor response recorded compared to that of the structure, the active control may not work efficiently. Okay. There is something called semi-active. This is an elevation of these two. So, you have a passive control mechanism also in place partly, and partly you have gotten actuators also. So, it is called semi-active control system. Okay. These are all very commonly used in land based structures, okay, especially to alleviate forces either from wind or from earthquakes. But the application of this is never being recommended and used in offshore structures at all for two reasons. One, people never felt that offshore structures require a response control. One can ask me a question counter, how people felt response requirement to be controlled in land based structures. Okay. For example, I think you will know in hotels in abroad, let us say, especially in European countries, as you go higher and higher, maybe 20th story, 40th story, their rent is half of the ground floor, okay, because it requires a lot of uncomfortability. As you go higher and higher to stay, the rent is practically half. So, people feel that the response on the structure under unexpected forces can cause undesirable movements, number one. And number two, many structures failed because of earthquake or lateral forces occurring from wind when there was no response control mechanism introduced in the system. Therefore, international courts came out with a stringent regulation that mostly all public buildings like schools, hospitals, etc., should have some isolation control mechanism in the system which can alleviate not 100%, but at least partially the unexpected design force on the system may be caused by earthquake or by wind. Earthquake means massive structures, wind means tall structures, because tall structures will have active wind force on the system. But this idea was not, let us say, applied upon or thought of in offshore structures, because people never thought that offshore structures will also have uncomfortability in terms of its production facilities. Now, this was improvised in ML80s because at 80s or early 90s people thought that ML80 is a very successive adaptation of a compliance system for deep waters, but it has got some demerit, it is having larger deck displacement, I want to control. Now, the displacements of two order here. One, the deck can move in the heave direction, which is vertical on the vertical plane. People are not bothered about this because the topside load is about 25,000 tons, which is very, very high, so it cannot be felt, right. But people are really bothered about the surge and sway motion or roll and pitch motion. Okay. So, roll and pitch motion will not occur because they are almost stiff degrees. Surge and sway are almost compliant degrees. So, the response compared to surge and sway will be larger with that of roll and pitch. Okay. Therefore, people entirely focused on controlling surge or sway motion. Surge will be for unidirectional, surge and sway will be for multidirectional waves. We already know this, is it not? Okay. So people thought about the response control applying specific degree of freedom in offshore structures. So let us see the type of control systems here. Passive controls are listed as base isolation, metallic dampers, friction dampers, viscoelastic dampers, tuned liquid dampers called as TLDs, and viscous fluid dampers. Active control systems are bracing systems, variable stiffness and hybrid base isolation systems. Semi-active are variable orifice devices, magnetorheological dampers, MR dampers, etc. All these are comprehensively available, discussed, applied, and you will ultimately see all of these kind of systems are available in all structural systems of mechanical, aerospace, etc. For example, a hydraulic door closer in a door has one of the mechanism systems here, okay, which is actually a spring mass system, which is nothing but a passive system. My door closer operates in a passive control system here. When I open the door, the spring applies the force opposite to it, the door closes. So all systems in reality, if you see, mechanical systems do have one of the control mechanisms implemented in them, okay, whereas structural systems have to be implemented by force. So offshore structures had an idea of implementation of passive control mechanism, which I will discuss here. So tuned mass damper, as I picked up from here, which is one of the, one can have a liquid damper, one can have a mass damper also. So TMD is one of the passive type of response control. So it is very simple. I attach a spring mass system to the primary system. So primary system M is capital M, the secondary mass is small m, capital K is for the primary system and small k is for the secondary system. Now obviously the primary system will or will not have a damper, okay. The secondary system may not have a damper at all, okay, it will be simply spring mass system. So now I can write an equation of motion of this system easily, because I have got 2 degrees of freedom y1 and y2. I can easily write equation of motion of this. I can solve this equation of motion and see what is the complexity to tune this. Now very interestingly, where you are going to tune this, it is very important. The primary system will have the maximum response only when it resonates. So the excitation force is P0 sin omega t, for example, or EI omega t, maybe sine and cosine components, both are present in the system for a given amplitude of P0. Now when the excitation frequency matches with the fundamental frequency of the primary system, the system will excite to its maximum. That is always, we know that, okay. So the idea is to control that maximum excitation. So we generally take care of dampers in the system, right, like C 2 zeta omega m, we introduce damping in the system 1%, 2%, 5%, etc., which are fortunately derived from hydrodynamic damping in offshore structural models, or one can also have external dampers which I am going to apply in this system here, okay. So the spring mass system of Km, which I call a secondary mass system, is actually nothing but an additional damper to the primary system, okay. So there is no requirement of an additional damper to the secondary mass system. So I do not have C2 here, I have only K1, M1 and C1, but I have only K2 and M2, I do not have C2 here, because K2, M2 itself is an integral C2 or damper to the primary system, okay. So I have a 2 degree of freedom system model here, can easily write the equation of motion and solve. The difficulty is when you have got to have the tuning of the secondary mass system to that of the primary system as an excitation frequency, this cannot be analytically studied, because you know at analytical equations, when this equation of omega equals omega bar, you will see it become unbounded, because the primary mass system does not have a additional damper, okay. Solution cannot be obtained. So you have to tune this using experimental methodology, by which what M2 versus M1 ratio, what omega 2 versus omega 1 ratio can be adopted for the given system, therefore the system of the response of the primary system can be minimized. So we did conducted experiments and obtain that parameter, substitute that parameter in equation of motion and solve, okay, because you cannot directly solve this in equation of motion for omega equal to omega bar, okay. If that is the case, even if you say omega 2 is equal to omega 1, even then it cannot be solved because they will resonate, okay. Most interestingly, one can physically ask me a question, sir, when you attach a secondary mass system to the primary mass system, how actually the response will get controlled, okay. You have to tune the mass, secondary mass, such a manner that they should be out of phase. On the other hand, if the primary mass moves to the right, the secondary mass should move to the left, so it should drag the primary mass to the left. On the other hand, when the primary mass moves to the left, because the wave can act in both directions, the secondary mass should move opposite to it and drag it back to the normalcy. So M2 and M1 or omega 2 and omega 1 should be designed in such a manner they should remain out of phase for the entire period of vibration. Okay. So it is very interesting problem. Physically you can see this. I will run a video now to show you how this can easily be seen. Then we will derive this mathematically. First let us understand the physical problem. Physical problem is I have an Km system, large displacement, I want to control. Okay. I am controlling by putting a secondary mass system to it. Now I cannot analytically solve this problem straight away because I am going to tune it to the maximum response of the primary system, which will happen only when omega equal to omega bar of the excitation frequency. So I have to do experimentally find out the parameter where I got to tune the secondary mass ratio with respect to the primary mass such a manner that they not only remain out of phase but also I will be able to get the response experimentally and therefore analytically. Okay, what are those parameters, how this equation becomes complicated and so on and so forth, we will just now see, but I want to run a video at this moment and see physically how this happens. Now you can see easily the leg is oscillating with respect to the hinged point, you can see the movement of the deck and unidirectional wave, it is actually a surge action. Okay. Now let us see more deliberately for a very low frequency. Okay. It has got a very beautiful motion in terms of pendulum action. And now I want to stop this because this is very large as far as the researchers are concerned. I want to stop this. Now I put a secondary mass system suspended from the primary mass and see what happens. Secondary mass suspended now, wave is applied, unidirectional, scale model of 1:100. Look carefully, when the system moves to the left, the pendulums to the right, you can see that. I will show you very interesting, the top deck does not move at all, only the pendulum is oscillating, you see. Okay, there is a response control obtained in this. It is a very simple mechanism by which I can tune the secondary mass to that of the primary mass so that they are out of phase and I can control the response of the deck. Now physically this is what it is, but the complication comes when you really want to write the equation of motion for this to solve. Okay. So the system has only one unique frequency which is to be tuned properly so that the frequency when it is excited the damper will resonate out of phase and the response is achieved. Energy is dissipated by inertia force and secondary mass attached to the structure. So these are examples of the problem. This is actually the physical model which has been done at IIT Madras. These are the dimensions of a scaled model, that is this system which is shown on the right hand side, and this has got very good references of Sara Marano which I showed you in the last class also. We have also published one paper on the same idea in 2010 which I am referring it for my results. So the present study actually proposed alternate solution in terms of tuned mass dampers. So I will stop the lecture here, then I will continue this lecture in the next class just to make you to understand how I do a equation of motion for the system available here, and then how do I solve, what are the parameters, what are the governing curves I get, and how do I actually tune to get my out of phase relationship between M2 and M1.